Okay, so we're going to look at linear momentum, and we're going to start by understanding what these equations mean. So over here we have G, which stands for linear momentum, is equal to the total mass multiplied by the velocity of the center of gravity. So when you have a system of particles, so let's say you have a ball over there and another one, and this is connected by a rod, right? Let's say that the rod is massless and this one has a mass m, that other ball also has a mass m. If you wanted to quantify how the entire system is moving, so let's say that this thing is translating and it's also rotating, right? But if we wanted to sum the motion of everything all together, what we'll do is we'll look at the motion of the center of gravity, G, right? So if you remember back to FSK, this is what we did basically. We always simplified everything to a single point particle, which was the center of mass of that particle, and we described how that thing moves. So the center of mass G describes how this entire object is moving, whether it's rotating or translating or whatever. It describes how this entire thing moves as a system. The problem with this is that if G only has a velocity, Vg, right, it doesn't capture that these two masses are rotating around G, right? So that'll be a problem when we come to angular momentum, but for linear momentum, for right now, it's not a problem. So linear momentum, we can break it down into the total mass of the system multiplied by the velocity of the center of gravity. So basically what we did in FSK, even if these two particles weren't connected. So let's say we had a situation like this, where one was going in this direction and one was going in this direction but much faster. So we'll call that V1, we'll call that V2. And then we can calculate the resultant velocity for the center of gravity, right? It's probably going to be something like that. We'll call that Vg. So again, even though these two masses aren't connected to each other, we can still quantify the mass of the entire system. And then, if I'm not mistaken, if you wanted to get the mass of the center of gravity, so Rg dot or Vg, if I'm not mistaken, that will be equal to the sum of the masses times their velocities over the sum of the masses. So it's basically the weighted average of the mass, of velocity. Yeah. So for this case, it'll be, I'm going to call that 1 and I'm going to call that 2. It's going to be m1 times v1, and remember it's a vector, plus m2 times v2 over m1 plus m2. So that will give you the velocity of the center of mass. Right. Cool. But yeah, in most cases it will be given to you, but if you ever need to calculate it, that's how you'd calculate it. And yeah, so the momentum of the whole system is given by this equation, right, where Vg represents the velocity of the whole system. And then in the case where let's say we were given the velocity of like each and every particle, so let's draw that situation again, where we had mass 1, mass 2, and it was translating with the velocity v, and then let's say it was rotating with an angular velocity of omega. Then we can use this equation to also find the linear momentum of the system, right? So to use this equation here, we're going to take the sum of each of the masses and we're going to multiply them by their respective absolute velocity, right? So let's say this entire system is rotating about its center of gravity g, and we wanted to use this equation here. So I'm going to call this particle 1, particle 2. Let's work out m times v for particle 1. Okay, so I'm going to first break down this equation. So this one is going to become m1 times v1 plus m2 times v2. So I'm just doing this calculation for both particle 1 and for particle 2, right? And we said that the rod is massless, so it's not going to have a momentum because its mass is 0. So even if we did, let's say we called the rod particle 3 and we said m3 times v3, this is going to be 0 because m3 is equal to 0, right? So we only have these two in this case. So we can break this down. Let's do particle 1 first. So we need to find the absolute velocity of particle 1, right? So what we're going to do is we're going to say v1 is equal to vg plus v1 relative to g. Okay. And if you look at this whole thing, right, this thing is basically translating, right? And it's rotating. So this is basically your fixed axis and it's rotating around point G, right? So its motion is summed up by G moving, right? G doesn't rotate around anything. Everything is rotating around point G, and all that G is doing is moving to the right. Okay, so Vg is just going to be equal to V, because point G is not going around a circle, or G is not going around a circle. G is just moving to the right hand side, right? The rest of the particles are moving with that same velocity and they're moving relative to G. So the rest of the particles are rotating. So particle 1 over here, particle 1 is going to have this velocity, because remember, everything is connected. So particle 1 has to move with the same velocity as G, but it's also rotating around G. So it's going to have some rotational component, right? But at the same time, it's moving with G. I hope that kind of makes sense. Okay, so we've established that Vg is equal to V. And then, since we have a rigid body, we can make this omega times r, where r is just going to be the distance between G and particle 1, right? So cool. If we know all of these values, we can solve for the absolute velocity of particle 1, and then just make sure to do it in vector form. And then we'll do the same for particle 2. So we'll say this is equal to Vg plus V1 relative to G, right? Looks like a 6. Okay, and then again, we're going to do the same thing, where this is just going to become V. Sorry, that's just V plus omega crossed with r, right? So you can see that we get the same equation in the end, but these are going to be in separate directions. Okay, so yeah, in the end, you'll end up with this being equal to that. So we'll take the mass of velocity 1 to find the momentum of the entire system, right? We'll say the mass of particle 1 multiplied by its velocity, which is going to be equal to v plus omega crossed with r, and then plus the one for particle 2, which is going to be the mass of particle 2 into v plus omega crossed with r. Now remember, these r's aren't the same. This is v2 relative to g, and then this is going to be r2 relative to g. So r2 relative to g, it's going to be in the opposite direction of the vector for particle 1. Right, so these will give you different signs. Okay, if you were to visualize it, it'll look like that. So you can see these are pointing in different directions, and then they also move with the velocity of v. Right, so cool. When you do that, we can simplify this, and you'll see that since we have these two, so this is going to be v2 relative to g, and this is v1 relative to g. If we look at the equation for v2 relative to g, it's the same magnitude because the radius is the same, right? Since it's just omega times r, right? Just in the opposite direction of v1 relative to g, which is also equal to omega times r. They're going to cancel out, right? So if I rewrite that, I'm going to get m1 v plus omega times r, right? And in this case, it's pointing in the positive direction. So I'm going to call this positive, and then I'm going to get a negative for my other case. So over here, I'm going to get m2 v plus omega crossed with r, right? Sorry, this is plus, right? And let's say that m1 and m2 were the same, then you could basically cross these two out. So this would be negative, sorry. But you don't really have to know that. If that was confusing, it's okay. You don't have to know that, just follow the steps and you will get to the same answer. So another thing, when to use which one. So if you have the velocity of the center of mass, just use this equation over here. Don't waste your time and break everything up and find the absolute velocity of each and every particle. And just use this equation over here. And then if you were given the absolute velocity of each particle, don't waste your time and try and find the velocity of the center of mass. Then just use this equation over here. Okay, but you can use either one and you will get the same answer. Okay, hope that makes sense. And then when dealing with a change in linear momentum, we use this equation over here. Okay, so we have the integral from t1 to t2 of g dt. So this represents the change in momentum over a given time, and that's going to be equal to the change in the sum of forces over a given time, right? Cool. So if we had a case where, if we wanted momentum to be conserved, so let's say we wanted delta G to equal 0. In order for this to be true, for this equation over here, we need our sum of forces to be 0. Okay, this is also a vector. So another thing we can do is split this up into its different components. So let's say we were only looking at the x component, right? Then if we wanted momentum to be conserved in the x direction, then we need the sum of forces in the x direction to be 0. If we wanted it to be conserved in the y direction, then we do the same thing, right? But then now our sum of forces in the y direction need to be 0. Right, so if sum of forces in the y is equal to 0, then this whole thing becomes 0, meaning that the change in momentum in the y direction will be equal to 0. Okay, so that's how you check for whether or not momentum is conserved in a particular direction. In order for it to be conserved in a particular direction, the sum of forces in that direction need to be 0. Okay, so let's try and apply that to an example. So over here we have 2 mine carts, one with 300 kgs and one with 400 kgs, the mass of 400, and then they're rolling in opposite directions along a horizontal track, and then they give us the speeds at which they're rolling towards each other. Then they tell us upon impact the cars become coupled together, and then they say just prior to impact a 100 kg boulder leaves the delivery chute with the velocity of 1.2 meters per second in the direction shown, right? And it lands in the 300 kg car. We are asked to calculate the velocity v of the system after the boulder has come to rest relative to the car, right? So we're told that upon impact, the cars become coupled. And then we're also told that this boulder over here basically falls into the cart, bounces around, and then it's going to eventually come to rest. And then the whole system is going to move in a particular direction altogether. So let's say it moves in this direction, right? All together as a unit, and we're asked to find that velocity of the entire system, right? So since we're basically given 2 states, right? So this is our state 1, and then state 2 was written in words where we say everything has been coupled together. So we're going to have cart 1, which is the 300 kg, and then we're going to have the rock, which is sitting somewhere there. Let me draw it like this. So we have the rock, we have the cart, and then we have the other cart. Right, and everything is moving together at a speed v, right? So that's our state 2. And then let's draw state 1. So we have the rock, we have the cart, the first one. Okay, that's going at that velocity, cool, and this is going at this velocity. Okay, this is state 1. So if we use the equation for momentum, which is that integral from t1 to t2 of g, dt, equal to the integral from t1 to t2 of the sum of forces dt. Okay, we want to look for a case where where the sum of forces is 0. Okay, so in case 1, there aren't any forces in the x direction, but there are forces in the y direction, right? So there's gravity acting on this object over here, pulling it down, and then there's gravity pulling this down, and then there's also a normal force pushing that up, right? And same for the other cards. So we don't want to take sum of forces in the y, because we're going to have to account for this gravitational force over here, right? So for sum of forces in the x, however, there aren't any forces acting in the x direction. There's no resultant force that's pushing this one that way. There's no resultant force that's pushing that one that way, right? We aren't told anything like that. So we can safely assume that the sum of forces in the x direction are going to be 0, right? So we're going to say that delta G in the x direction is equal to 0, because the sum of forces in the x direction is equal to 0. Okay. Let me just move this question down. Okay. Cool. Then what we need to do now is we need to find G1 and G2. So this equation over here can be simplified to G2, which is our momentum at state 2, minus G1, which is our momentum at state 1, is equal to 0, which means that the momentum at state 1 is equal to the momentum at state 2. Okay, so let's find the momentum at state 1. Okay, so the momentum at state 1, remember our momentum is equal to m total times the velocity of the center of mass, or it's equal to the sum of each of the masses times their respective absolute velocity, right? So and this is for G as a vector, so both x and y components. Okay, so in this case, we're given each of the individual velocities, right? So I'm not going to waste my time and try and calculate the velocity of the center of mass and then use this equation over here. I'm rather just going to substitute everything into here, because I'm already given the velocity of each and every particle. So I'm going to say that g of x, right, because I know in the x direction it's conserved, so I'm only going to work with x components of velocity. So g of x is going to be, g of x1 is going to be equal to mass 1, and I'm going to call that this 300 kg cart. So it's going to be 300 multiplied by 0.6, right? And then I'm going to add to that the momentum of mass 2, which is going to be 400 times negative 0.3. So we also have to consider the direction in which it's going, right? So negative 0.3, then plus the mass and velocity of this of the rock. So it's going to be 100 times, and then we're given, if I'm not mistaken, we're given this angle here to be 30, right? Yeah, so we're given this angle 30, and then opposite angles, meaning that angle there is also 30. Okay, so it's going to be positive 1.2 cos 30. Okay, and then that will give you your momentum in the x direction for T1 or gx1. And then for gx2, right, for gx2, everything is moving together at the same velocity v, right? So in this case, I have the velocity of the center of mass because everything is moving together, meaning that the center of mass itself will be forced to move at the same velocity. So yeah, I hope that kind of makes sense. So if I told you, if you go back to FSK, let's say you had a block, and let's say that block was moving at a velocity v, right? Every single point on that block, right? Let's say the block was filled with marbles, right? Or like, let's say this is a box that's filled with marbles. If the marbles don't slide around and they're stationary, then every single individual marble is going to be moving with the velocity v, right? And let's say that the center of mass of the system was here, right? That too would be moving with the velocity v. Every single point has to move with that same velocity, right? So we kind of have the same situation here where every single thing is forced to move with the same velocity. So the velocity of g in this case is going to be equal to v, right? And we don't know v in this case because it's what we're trying to solve for. So we know that gx2 is going to be equal to m total multiplied by vg, right? And m total is just going to be 400 plus 300 plus 100, and all of that multiplied by v. So that's gx2. And we know that since momentum is conserved, we know that gx2 is equal to gx1. And then we can calculate what gx1 is, and then we substitute this equation for gx2 and we solve. Okay, hope that makes sense. And then this is another question. So in this case, we're given a system of particles, right? And we're not going to do the angular momentum for this video. We'll do it when we cover angular momentum. But just looking at the linear momentum of the body, we're told the velocity of Vg. So the equation that we're going to use is going to be G is equal to m total multiplied by Vg, right? And we're told that it has 5 particles and each particle has a mass of 5 kgs. 0.5 kgs, sorry. Okay, and then, yeah. So you basically just use this equation. You're going to say 5 times 0.5 times whatever Vg is. Right, and they give you the magnitude of Vg. So it's going to be equal to 5 times 0.5, right? And then the magnitude of Vg, which is 4, and then into the x component is going to be so the total angle over here, that's also going to be 15 degrees. So this total angle is going to be 30 degrees. So it's going to be cos 30 and then sine 30. Okay, and then that will give you the linear momentum for this question over here. Cool. Hope that makes sense.